Sir, good morning, sir.
Good morning, sir.
Sir, we will start within your 5 minutes, sir.
Sure, sir. Yeah.
Yes, sir. Sir, let me start the session, sir.
Sure, sir.
Yes, sir. Very good morning to all gathered here. I would like to welcome all the participants for a AICTE sponsored 6 days online short-term training program on emerging trends and challenges in a VLSI mixed signal processing for a fourth industrial revolution. Welcome you all. It's my pleasure to welcome our today's resource person, Mr. Samuel Jigme Harrison, ST Microelectronics Asia Pacific Private Limited, Singapore, who is going to handle the session on the topic of physical design and its role in the semiconductor industry. Welcome you, sir.
Yeah, thanks, sir, for the introduction, and my heartfelt thanks to Kongunadu College of Engineering and Technology for inviting me as a speaker for today's session.
Hi, sir. Before going to session, let me see the short intro about our resource person.
Good morning to one and all gathered here. It's my immense pleasure to welcome our today's resource person, Mr. Samuel Jigme Harrison. Before going to our session, let me see the short intro about our resource person. He started his engineering education from St. Joseph College of Engineering, Chennai, with a bachelor degree in the field of electronics and communication between 2004 and 2008. He then completed his master in science, specializing on integrated circuit design, a joint degree from Nanyang Technology University, Singapore and Technical University of Munich, Germany in 2010. He also holds a master in business administration from Anglia Ruskin University, UK. During his studies in these three institutions, Samuel published journals and papers in different conferences and national level symposiums. Samuel started his career with Avaho Technologies Singapore in 2010 as an entry level IC design engineer. He then got promoted as a senior ASIC design engineer in 2014 and the company was renamed as Broadcom Limited Singapore in 2016. He is currently working with ST Microelectronic Asia Pacific Pte Limited, Singapore since 2017 as a senior digital IC design engineer. He has 10 years of experience in VLSI, specializing in physical design implementation with 90 nanometer, 65 nanometer, 40 nanometer, 16 nanometer, and 7 nanometer technologies, covering areas like floor planning, place and route, clock tree synthesis, static timing analysis, and physical verification. He received a Technical Merit Award in SNUC 2018 conducted by Synopsys for presenting a paper, and his membership professional bodies like Indian Society for Very Large Scale Integration Education, VLSI Society of India, Semiconductor Society of India, IEEE, MIET, SSIA, AIES, IDRC. In this way, I would like to hand over this session to our today's resource person, Mr. Samuel Jigme Harrison. Please, sir.
Uh, Thank you, ma'am, for the introduction, and welcome you all to this session on physical design. And I hope that this session will be helpful for each one of the participants who are attending this session today. Okay, let's move on to the presentation for today's session. Okay, so today's session is VLSI and physical design and its role in the semiconductor industry. Okay, so before moving on to the topic, let's deal about some information about the semiconductor industry in Singapore. The first semiconductor organization was opened in 1968, and Singapore houses more than 60 semiconductor companies employing around 35,000 people. So this is a very big industry in Singapore, and the semiconductor industry also contributes to around 7% of the country's economy. So there are lots of manufacturing facilities and also design houses in Singapore, and the government is taking care of giving grants and also bringing up new facilities for both design houses and the manufacturing sector. So my workplace, I work with ST Microelectronics. ST Microelectronics is a Europe company, and it's Europe's largest semiconductor chip maker and one of the world's largest semiconductor companies with its corporate headquarters at Geneva. So we serve around 100K customers around the globe with 11 manufacturing sites. and we serve like most of the major uh, companies like Apple and the Apple watches, iPhones have ST chips in it. And we have around 46,000 employees worldwide with 18,000 active patents. Okay, so moving on to today's topic, like what is physical design? Physical design is actually the process which transforms a digital circuit into a layout. For example, in the IC design flow, you have a front-end team who works with VHDL Verilog coding to bring up a netlist, and it is a circuit representation, and we transform it into physical layout in the physical design team. So this circuit representations are converted to geometric description of shapes with various metal layers. And when manufactured, the metal layers will ensure the functioning of the circuit. For example, if in the netlist we have an input pin which is A and output pin which is B, and if there is a connection in the netlist in the circuit, so in physical design, the connection is being replaced by metal layer. So A is the input pin and B is the output pin, and the metal layer exists as a connection between these two. So now the netlist is converted to a physical layout. So this is actually a representation of how the netlist is being converted into physical layout. Okay, so in this diagram here, you can see that there is a system specification given to the architectural team. The system specification is given by the customer, and then the architectural team gives the data to the functional and design and logic design team, where the circuit is being designed, and you have the inverters, NAND gate, NOR gate, etc. And this circuit is given as an output to an input to the physical design team. So the physical design team goes through all the 6 phases, which is partitioning, floor planning, placement, clock tree synthesis, signal routing, and timing closure. So all these steps are performed in physical design, and then the next step is physical verification, where we check for DRC, LVS, ERC. All these checks, we will be going into it in detail in the next few slides. And then from the physical design team, the chip is given to the fabrication plant. So the fabrication plant is where the chip is manufactured, and from the fabrication plant, the chip is given to the packaging and testing facility. So here they do the packaging, and once the packaging is done, all the pins are connected to the board, and the test is being performed to make sure that the functionality of the chip is correct, and if the chip is working. Because when we manufacture a chip, where they manufacture it in the form of a wafer. So in the wafer, there are lots of chips being put into it. So one may work, one may not work. So all this testing is being done to ensure that the chips are working. So and after the testing facility, it is given to the customer. So this is how the IC design flow works. So now what is the input to physical design? The inputs to physical design are a netlist, library information of cells in the design. So each cell in the design, which is a standard cell, will have a library information. It is known as .lib, and they will have the timing information in the .lib file, and a technology file with the manufacturing constraints and timing constraints. So technology file is provided to you from the foundry, which is your manufacturing fabrication plant. So for example, if we work in 40 nanometer technology, we need to make sure that we receive the 40 nanometer technology file. So we will have the manufacturing constraints and timing constraints. Next is timing, power, and design constraints are to be met during physical design. So these are the main criteria to be checked during physical design, which is timing, power, and design constraints. So what are the steps in physical design? The main steps in physical design are floor planning and power planning, placement, clock tree synthesis, routing, static time analysis, and physical verification. So all these steps um, are combined together to form the physical design flow. So as a physical design engineer, we need to be aware of all the steps in physical design, and we need to have in-depth knowledge of each step. So first one is floor planning. So floor planning is the first and foremost step in physical design. And what are the goals of a good floor plan? So floor planning in physical design is similar to a floor plan, floor plan of a house. So first the architect comes up with a floor plan, like where to place the hall, where to place the dining room, and etc. So this same idea is behind the floor planning in via physical design, where the engineer has to come up with an idea to place the macros, to place the pins, to provide routing channels for the tool. So all this idea has to come as an initial uh, phase in physical design. So what are the goals of a good floor plan? Minimized total chip area, routability of the design, minimal congestion, and low power consumption. So goals of a good floor plan include minimized total chip area. These days, the customers and the companies, they look for chips with less die size area. So they always prefer the engineers to design chips with minimized chip area. So this actually will enable the companies to spend less during manufacturing, and also it will help in the applications also. So goals of a good floor plan also include routability of the design. So when you do your floor planning, we need to make sure that the design is routable, and based on the routing resources, we need to make sure that we design a good floor plan, and there should be minimal congestion in the design. So we need to make sure that all the macros and all the pins which we place do not provide any congestion in the design. And the final one is low power consumption. This is a very important feature when it comes to floor planning, because these days the distance between the source and drain is less, and so we work on advanced technology nodes where there is chances of high power consumption. So we need to work on a good floor plan to ensure we have low power consumption. So what are the steps in floor planning? The size of the chip is determined, and IO pin placement is done, macro placement is done, creating standard cell rows, and adding routing and placement blockages. So these are the steps in floor planning. So with a view to determine the size of the chip, floor planning can be controlled by the following two parameters, which is aspect ratio and core utilization. So aspect ratio is actually the width to height ratio of the chip. So the first step in floor planning is to determine the size of the chip. Only when you have the size of the floor plan, the chip, you can proceed for the next step. So width is related to horizontal routing resources, and height is related to vertical routing resources. So in the chip, like you will have routes in both horizontal and vertical directions. So we need to make sure that we have proper vertical routing resources and proper horizontal routing resources. Now the aspect ratio is equal to number of horizontal routing resources by number of vertical routing resources. So if your aspect ratio is equal to 1, then the block shape will be a square. If your aspect ratio is greater than 1, then the block shape will be rectangle with more routing resources in the vertical direction. So your height is greater than your width. And if your AR is less than 1, then the block shape will be a rectangle with more routing resources in the horizontal direction. So your width is greater than your height. So this is the theory behind aspect ratio, and it helps you to determine the size of the chip. Next is core utilization. The area occupied by the standard cell and macro, that is the percentage of area used for cell placement. For example, a core utilization is equal to standard cell area plus macro area by the total core area. So in order to have proper routing resources and less congestion, we need to analyze the floor plan initially when we determine the size of the floor plan. So we are aware of the number of macros to be placed in the design, and each macro will have X and Y. So we can find out the width and height of the floor, the macros, and you can make a calculation like how much space is it getting occupied and how much density it takes in, and you can calculate the area for the macros, and then you know the standard cells being used. So the standard cell area has also been calculated, and based on it you can make an assumption like how much resources are left for routing. So if the core utilization is 0.6, it means like 60% of the area is already used for cell placement. So cell placement cannot be avoided, and your only 40% is left out for routing of signal and clock nets. So if your core utilization is like 0.7, like then it means only 30% is available for routing, which is quite tight. So we need to make sure that we always have a core utilization between 0.6, 0.5 to 0.6. 0.5 is quite advisable, and the maximum we can go is 0.6, so that you will have more resources for routing. Otherwise your design will be too congested and you will have hard time fixing DRC violations and timing violations. Core rows. The height of standard cells like determine the spacing between the core rows, and these core rows actually are drawn throughout the floor plan in horizontal direction. So the standard cells are placed in these core rows. And if you analyze the floor plan, you will see that alternate core rows are flipped to change the row orientation. So why do we flip the alternate rows? For example, if you have a core row with VDD and ground of the standard cell, VDD is at the top of the standard cell and ground is at the bottom of the standard cell. So when you place the standard cells neatly on the core row, one row is placed, and the bottom next row of core row we have to place the standard cells. So when we place the standard cells in the next row, if we place the standard cells without flipping it, what happens is the bottom ground of the first of the standard cell in the first row will overlap the VDD of standard cell in the second row. Because when you place the core rows and when you place the standard cells without flipping it, it will overlap, so that the ground of the ground of the standard cell in the first row will short with the VDD of the standard cell in the second row. So in order to avoid this short, what we do is alternate rows are flipped, so that when we place the standard cell in the second row, it is flipped. And to make sure that the second row will have all the standard cells in a flipped manner, so that the top of the standard cell will have ground and the bottom will have the VDD. So the top of the standard cell, it has ground now. So the first row, the standard cell in the first row has ground at the bottom, and the standard cell in the second row has ground at the top. So when they overlap with each other, it is neatly placed and there is no short. So that is the main reason why we flip the alternate rows in floor plan step. The spacing between macros. A minimum spacing must exist between macros for pin sites. So you have channel spacing here, and channel spacing equals the number of pins into pitch by available layers um, by total layers. So the pitch should correspond to the topmost metal layer. For example, when you have two macros next to each other, and you need to determine the channel spacing between them. So if one macro has metal 4 as the pin and other macro has metal 3 as pin, so when you calculate the pitch, your pitch should correspond to the highest metal layer, which is metal 4. As far as possible, open spaces should be avoided in the floor plan. The pin of the macros should also face the logic area. So if the pin of the macros face the boundary of the chip, then during routing, the tool will have to take long routes. So but when it is facing towards the logic area, the routes are shorter and the communication channels are straightforward. So when you start floor planning, you can get your data flow diagram from the customer. So the customer will provide a data flow diagram, and this data flow diagram will have a detailed layout, like which macro communicates with which macro, which macros are grouped together. Like all this information will be there, so that it is easy for you when you start your floor plan as a first step. And when you click a macro, a memory, some blue lines will be displayed. These blue lines are known as fly lines. So the blue lines will determine you and show you that like which macro communicates with which macro, and so that based on the fly lines you can also place your macros in floor plan. So you need to make sure that the routing channels between macros is big enough to accommodate the signal routes and power stripes. Now macros can also be abutted with the pin sides in the opposite direction. So blockages, there are two types of blockages, which is placement blockage and routing blockage. This prevents a placement of standard cells, buffers and inverters. So in your floor plan, once you complete your macro placement, if you find that there are some places where there are very minor spaces available, you need to put a placement blockage, so that during placement step, the tool, when it tries to place the standard cells, it will not place the standard cell in that particular region which has small spaces in it. So that we need to make sure that we force the tool to place the standard cells only in the center of the chip, and all the surrounding area is being filled with macros, or the small areas are filled with placement blockages. And routing blockage, this also prevents routing of metal layers in a particular region. For example, if in a particular region, if you don't prefer to use metal 4 route, you can draw a routing blockage, and you can select an option that the routing blockage will block the metal 4 routes alone. So in that region, all the layers can be routed. For example, if you have 6 layers, metal 1 is for power and metal 6 is for power. Metal 5 is for clock routes. So metal 2, metal 3, metal 4 is for signal routes. So in that particular region, you can block your metal 4 route alone, so that metal 2 and metal 3 will be routed. So that is why we use routing blockage. So placement blockage and routing blockage are very important in physical design. Placement blockage will help you even to reduce the density of the chip. If your placement blockage is not correct, then it will create unnecessary DRCs and unnecessary density problems. So this is actually in an Innovus GUI. So for physical design, we either use Innovus from Cadence or ICC2 from Synopsys. So majority of the companies, they stick to Cadence and they use the Innovus tool. So this is how an Innovus GUI will look like when you open it in your database. So at the top, you have a menu bar, and here you have toolbars where you have an option to scale, draw a net, place a via, cut a net, move, And also here you have an option to select, deselect. Here you have option to select the colors for the highlighted net, etc. Zoom and zoom out. And top you have the main menu bar, and at the top you have the name of the database. So this is very important as a physical design engineer. When you open a database to fix some issue or to analyze a data, you need to make sure that you have opened the right database. So if you have opened the correct database, you can double check at the top that the name of the database to make sure that you are working on the correct database. And also these are the design views, and this is an online help. Here you have a layer control bar where you have options to select standard cells, deselect standard cells, enable physical cell, enable blockages. Here if you click the plus sign, there will be individual options for routing blockage and placement blockage. So you can select it, deselect it accordingly, and to check whether the floor plan, the design has the routing blockages enabled or not. And here you have congestion. So when you click the plus symbol, you have congestion maps being displayed. So you can understand the congestion of the tool, the floor plan, and also here you have individual metal layers. So you can select, deselect these metal layers to when you debug something in the GUI. And now you have a status which is routed. So routed is this database is routed. So it will show us a routed database. And here you have coordinates. Like if you keep your cursor here, it will point out the coordinates. So this is easy for you when you compare this result with a GDS later. And also here is a query button. Like if you click this button and if you place your cursor here, it will pop up a message saying the name of the cell and also the input output details of this cell and the XY. And here when you click this instance, here it will show the net, the instance name. And when you click a net, here it will show the net name. So all these are just basic idea of how a GUI will look like, and it will help you when during your analysis. So this is how a design is being routed. And here you can see that you have the macro standard cells here, and you have VDD and ground power stripes around the macro. So these VDD and ground power stripes around the macros, these thick layers are known as block rings. So they are present only around macros and IPs. And here you can see the internal pins of the standard cell IPs are connected to pins here, and here they are the pins placed during floor plan step, and all the routes are being drawn. So this is just a basic idea for you to understand and see how a design is being routed. So during floor plan, your macro placement will look like this. For example, if you have a group of macros communicating with each other, so they are, all those macros are combined together, and they are you can see that they are in the form of an orange color pattern. Here they are the form of a gray color pattern and a blue color pattern. So all these are communicating with each other. So we place them together. But in the this will actually help you for effective macro placement, and you can see that you have a very big space in the center of the design. This will help you to do an efficient placement of standard cells. Okay, next is power planning. So floor planning and power planning are one step together, but in this presentation we will be discussing power planning separately, because there are many steps to be taken care of during power planning. Okay, so power planning, what are the goals of power planning? To make sure that the power mesh is properly created, and all the standard cells and macros should get the required power supply, and we meet the IR drop budget. So for power planning, we need to make sure that there is a proper power mesh drawn in the design. So once your floor planning is complete, you have to make sure that power planning is done properly, so that the VDD and ground power strips which are drawn over the entire design is properly created. And all the standard cells and macros will have VDD, VSS pins. So we need to make sure that they all get the required power supply. So when you meet the first 2 points, your IR drop budget will automatically be good, and there will be less IR drop in the design, so that there are less hotspots during power analysis. So what are the power plant components? We have block ring. Block ring is the one I showed you before, like around the macros and IPs, you have VDD and ground power structure, and the core ring is the um, power stripe which is drawn at the boundary of the chip, and the routing standard cell pins, like all standard cells are in the core rows, and they are connected to the power rails using the M1 pins, and you add VDD and ground power strips in the core area. So and also we connect the pad pins, connect block pins, and the global net connections. So basically, as a simple understanding, we need to make sure that all the VDD and VSS pins in the floor plan, it may be a standard cell, it may be an IP or a macro, should be connected to VDD and ground. So all the VDD and ground pins should be connected. So this will ensure proper power planning. Okay, the next one is power pads. So power pads are placed in the design. They supply power to the chip. So power pads are either they are VDD and ground. So this is actually, if you have one common power supply, like VDD is 1.25 volt, then you can have just one VDD and one ground pad. What if there is a multiple power domain in the chip? So if there are 2-3 VDD power domains, then there will be VDD, VDD1, VDD2. So we need to make sure that all the power pads are placed properly, and the power is connected to the correct power pad. So some macros will be having 1.25 volt power, and some IPs will be having 1.5. So we need to make sure that they are properly connected to the respective power pads. And block power rings are the ones which I mentioned earlier. They are power stripes around the macros. So the width of the power stripe and the spacing between the power stripes are calculated by the designer. So for example, here if you see that the spacing, the thickness is different compared to the normal routes. So all this has to be determined by the designer. So this can be obtained from a reference from your previous projects, or you can discuss this with your power analysis team, so that they will give you an idea of how much width can be used as block power ring. The horizontal and vertical power stripes. These are the main power stripes which flow through the entire chip, and the VDD and ground power stripes run over the entire section. So horizontal wires are known as stripes, and vertical wires are known as trunks. The block rings, the standard cell power rails, are connected to the power pads through the VDD and ground power stripes. So it actually, the power planning is occurs in levels of hierarchy. Like for example, the initial one is you need to connect the standard cell M1 pins, which is the power pins. Standard cell should be connected to power rail, and this next step is the block rings should be placed, and the third one is to draw the main VDD and ground power stripes. So it is like internally connected with each other. So these power stripes use the widest and highest routing layer. For example, if you have 6 metal layers in your design, your VDD and ground power stripe will be metal 6. Why do we use the highest metal layer? Because for the highest metal layer, the width is more compared to the normal routes, and when your width is more current flows through, and there is less resistance. So that is why we use thick layers for power stripes. So when you have 6 layers, metal 6 is used for the VDD and ground, the thick power stripes, and metal 1 is used for connections to standard cell pins. So VDD and ground connection to standard cell. Metal 2, metal 3, metal 4 is used for signal routes, which occurs during the route step, and metal 5 is used for clock routes. So this is how the entire distribution of metal layers happens in a chip. But there are some chips which even has 13 metal layers. So they have more routing metal layers for signal routes. Okay, these are the standard cell rails. So as I mentioned earlier, that we have core rows where the standard cells are placed. So actually these core rows will have metal 1 stripes which connect to the standard cells. So they are used to supply power. The cells are connected to the rails through the follow pins. So the follow pins are actually either in metal 1 or metal 2. So here you have the follow pins are nothing but metal 1 pins which are supplied with power, and they are actually used to power up the standard cells. So all the standard cells in the design should be connected to metal 1 so that VDD and ground is being supplied to the standard cells. So as I mentioned earlier, the row orientation of alternate standard cells is flipped, and we know the purpose behind it. So IO pad placement. So IO pads are very important components in a chip, and we need to ensure placement of sufficient number of VDD ground pads on either side of the chip for uniform power distribution. And power consumption and IR drop should be taken into consideration while deciding the number of VDD and ground pads in the design. So the number of VDD and ground pads is decided by the architectural team and the power analysis team. So they come up with the number of VDD and ground pads based on the size of the floor plan. So we need to make sure as physical design engineers that proper connectivity from ground and VDD pads to the entire area of design is ensured for the success of the chip. So this is actually a pictorial representation of how power planning is done. Like you have VSS, VDD around the chip, and you have the VDD, the pads here. So you have the trunks and the stripes, and here internal to the chip, you have all the VDD and ground major power stripes, and the ones in yellow is the standard cell rails where the power connections are done through the M1 follow pins, and here you can see the standard cells. So the standard cells are getting their power. So all this is a bottom up approach. Like initially it is in the power distribution is in a hierarchy manner. So in Innovus, your power distribution will look like this. Around the block ring, around the blocks, you have the block ring now, VDD and ground is drawn. So VDD and ground in horizontal direction is metal 1 and vertical direction is metal 2. And here you have your standard cell rails with the metal 1 structure. And here you can see that your top layer is connected to ground, your bottom layer is connected to VDD. So when this metal 1 gets connected to metal 2, there is a drop of VI. VI is actually an interconnect between metal 1 and metal 2. So when you extend your metal 1 to this region, the tool will automatically drop a VI so that the connection is established between this ground and this ground, even though they are of different metal layers. So if you extend it here and if there is no VI present, then even though your connection is complete, there won't be any connection present because there is no VI present. And here also you can see that this top layer is connected to ground and bottom layer is connected to VDD. And now the standard cell is also connected to power. So here your block power ring is complete. Your standard cell is also completed its connection to the power, and also you have VDD and ground power strips. The major VDD and ground power strips which runs through the block. So your power planning is complete now, and you have ensure that all your components in the chip are connected to power. Okay, the next step is placement. So placement is actually the third step in physical design, where we take care of placement of standard cells. So what are the objectives of a good placement? Timing and power, minimum cell density and pin density, and routable design, and there should be a good control over congestion. So you do a good floor plan, and once placement is complete, if there are lots of congestion issues, then you cannot proceed forward for the other steps. So an objective of good placement is timing should be good, and your congestion should be controlled, and there should be minimum timing DRCs. Timing DRCs are nothing but max transition, max capacitance violation. So what are the steps of placement? There are 3 steps in the placement of standard cells. These 3 steps are actually internal to the tool. So only when you run placement, you can see these steps occurring in the log file for each, which is present inside your placement directory. So the first one is global placement. Global placement actually takes around 50% of the runtime. So global placement is simple. The tool will find an approximate location for each cell based on timing and congestion. So the tool will just put in the cells into the floor plan based on timing and congestion. So now in Innovus, almost all the placement engines are timing and congestion driven. So when the tool does placement of standard cells, it will take into account, it is aware of timing and also is aware of congestion. So timing is and congestion is already taken care by the tool. So the place cells are just in a random location. So they will actually overlap each other and they do not align with the power rails. So this placement technique is quite fast and accurate for the initial timing and congestion analysis. But there are lots of overlaps in the design and we need to fix it in the next step. So this is actually a representation of global placement. And here you can see that all the cells are randomly placed. They are overlapping with each other. They are not also placed on the standard cell rows. They are like outside the standard cell rows. So they are not properly placed. Their tool just puts in all the cells into the design, but it is not properly placed. So the second step is legalization. Here actually the tool moves the cells to the legal locations, the correct locations on the placement grid, and it overlaps the eliminated between the cells. So here actually it legalizes the cells and makes sure that it is placed properly. Cells are also aligned to the routing track. Cells connect to power and ground rails. So the third step is detailed placement. This actually takes place at the last phase, and it actually takes around 50% of the runtime. So this is also a step where minor modifications is done in the locations of modules, and standard cell placement is finalized here. So the main step occurs only in legalization, where proper placement of standard cells is done, and the cells are aligned to the routing track, and they are properly connected to the standard cell rails for power. So the next step is placement bounds. Placement bounds are nothing but placement groups. For example, this constraint actually controls the placement of a group of standard cells. For example, during standard cell placement, if a particular group of cells communicate with a particular macro, and if we don't group them, the tool actually will place them far apart from the macro, and they will be also be scattered all over the chip. So when we group them together in a certain location, the tool will actually place the cells in that particular location provided by the designer, and it will be close to the macro. So this actually is used to minimize the wire length. So when they are scattered all over the chip, during routing, there will be long wires come in the design, whereas this will actually enable the tool to use short wires. And when the wire length is short, your timing analysis is easy and your timing can be met. The next is addition of spare cells. These spare cells are also part of the standard cell library, and they are dummy cells which are inserted in the netlist. So the spare cells actually they don't have any function in the cell. They are actually they are part of standard cells, and the main reason why we put in spare cell is later during once we release the chip and the customer comes up with a new addition, new feature being added. For example, we have iPhone 10 and there is some feature added and iPhone 12 comes out. So same thing, it happens here when there is one version out and the customer comes back to the engineers saying that we need to add this feature in. So to add the new feature in, we need to have dummy cells in the design. Only then we can replace the dummy cells with the new feature in. So new feature will be in the form of some AND or not gate or NOR gate or something. So we need to add that feature in and remove the and we need to add that feature in. So in order to add that feature in, we need to have dummy cells in the design. Only then we can replace the dummy cells with the new feature. What if we don't have any dummy cells, any spare cells in the design? In that case, a new version cannot be implemented. So this is a main drawback here, and we as engineers, we need to make sure that the spare cells are always placed in the design. So they are used to accommodate future functional engineering change order, which are ECOs, after the tape out of the chip. So this is an example for good placement and bad placement. Good placement is here. You see that the macros are placed properly and there are wires being connected in between, and you can see that they are neatly placed. Whereas here for bad placement, you can see that there are lots of crisscross happening, and here you see in good placement the pins are properly placed, and so there is neat connectivity. Whereas here you see that the pins are clustered at one region, and you see their long routes go all over the chip. So this will actually cause a lot of congestion and timing issues and shorts and spacing violations. So we need to make sure that we have a very good placement, and to achieve a very good placement, we need to have a very good floor plan. So all the steps in physical design are interconnected, and we need to make sure that each step is done perfectly. So good placement and bad placement. A decrease in area and length of wires is comes under good placement, where in bad placement there is increase in area and length of wires. Routability is easier in good placement, whereas routability is difficult in bad placement. Shorter wires are used in good placement, so there is less power consumption. Because always when we have long wires in the design, it will add more power, consume more power. So the main advice is we need to make sure that we have shorter wires as possible. And longer wires result in high power dissipation. So good placement and bad placement. You have good placement, you have less hotspots, and less hotspots result in maximum performance, and bad placement has more hotspots, and here you have performance degradation. Congestion is a very important feature to be checked in placement step. So congestion occurs after placement step if the number of available routing resources is less than the required routing resources. So once your placement step is complete, we have a log file with the setup timing, because in placement step we only check for setup violation because the clocks are not propagated yet. So clocks are still ideal in setup in placement step. So we check for setup time, and then we also check for horizontal and vertical congestion and density. So horizontal and vertical congestion in the chip at placement step should be less than 1%. So so this actually will enable you to have less congestion issues during the next few steps. And congestion map is also available in your Innovus GUI. So based on the congestion map, you can see the hotspots present in the design. So this actually shows the different level of overflow in the selected layers. So what are the reasons for congestion? The reasons for congestion are high standard cell density and no proper placement blockages. So that is why I mentioned earlier that placement blockages and routing blockages are very important in the design, and the less routing resources will result in more congestion. Placement of macros in the center of the chip, which is not advised. And we need to ensure that during placement step, the tool should not do add additional cells or additional buffers to fix complicated timing issues. So we need to check the log files periodically to make sure and see the number of cells being added, because during placement optimization the tool may add lots of new cells. So we need to understand why the tool is adding new cells, so and how it can be avoided, because when you keep on adding cells in the design, it will create more congestion and it will start to consume more power. Okay, the strategies to fix congestion. Identify areas with low utilization and modify the floor plan accordingly. You have to spread out the top level ports so that there is less congestion next to the ports, and also you can increase the spacing between macros. You can add proper blockages and halos. Block resizing to reduce overall congestion, and the macro pins should also face towards the logic region. And now you can see that your placement of standard cells is complete. Like here, you can see that your standard cells are placed in this region, and these are the power routings that are internal to the standard cells in metal 2, metal 3, etc. Here, if you see, you have few empty spaces. So these empty spaces will be filled in during the route step. And during placement step, the tool will also do a trial route. The trial route is to show you that this is how the design will look like after routing. So it is not a real route. It is just a trial routing of the signal nets in the design. So for example, all the pins are routed and you can see the connections, but this is a trial route. The next step is clock tree synthesis. So we have clock tree synthesis, we have routing, we have static time analysis, and we have physical verification. So clock tree synthesis is nothing but you have a clock source and you have all the flip-flops in the design. So without clock tree synthesis, what happens is there is a signal communicating with this flip-flop and there is a signal communicating with the last flip-flop. So you can see that the distance between these two is different, and it's the delay is a lot. So when you have this kind of structure, that then it is difficult for the tool to balance this flop with this flop. So what happens is it creates timing issues and you're not able to close timing. So the clocks are not balanced, because in digital design, the main component is the clock. So how do we fix this issue? We do clock tree synthesis. Okay, so in clock tree synthesis, you add clock buffers and inverters internal to the circuit. So this will actually boost up the delays in the long routes, so that it will create a balance. So what are the objectives of clock tree synthesis? The objectives of clock tree synthesis is to attain minimum skew, minimum insertion delay, maximum transition, maximum capacitance. So these are the objectives of clock tree synthesis. So what is the effect of clock tree synthesis in the design? During clock tree synthesis step, lots of CTS buffers and inverters are added in the design. So this will actually result in more congestion and also more power consumption. So because the clock buffers and inverters are bigger in size and they consume more power. So how is CTS achieved? Clock tree synthesis is very important in majority of the companies, but some companies they also release the chip without clock tree synthesis. It is based on the complexity of the design. So they can also perform physical design without clock tree synthesis. But majority of the companies, they perform clock tree synthesis, and they have a hard time balancing the clocks and achieving timing. Now, how is CTS achieved? You add buffers, clock buffers and clock inverters. They are not the normal buffers and inverters. They are specific clock buffers and clock inverters to minimize the skew, to meet the max transition and max capacitance violation, and to balance the clock. And also non-default rules is also applied to the clock nets. So this we will look into it in the next slides. So what are clock buffers and clock inverters, and how is it different from the normal buffers and inverters? Clock inverters actually are used for clock tree building, and the clock buffers are used for balancing. The clock buffers are different from the normal buffers because clock buffers have equal rise and fall time, and normal buffers do not have equal rise and fall time. So when you have equal rise and fall time, it is easy for you to balance it. That is why we use clock buffers. Clock buffers are increased in size than the normal buffers. Here you have an example for launch clock and capture clock, and the delay developed in the transmission of the signal. So here you have a launch clock, and there is a combinational logic in between, and you have a capture clock. So the delay from launch clock to capture clock is the skew. So to have a minimal skew, we need to make sure the launch clock and capture clock are close to each other, and the combination logic are less, so that you have lesser delay. So what is min delay and max delay? You have a launch clock here, you have a capture clock here. So this is the min delay from the source to the rise time is the min delay, and the delay for one clock cycle is the max delay. So max delay is nothing but the delay for one clock cycle. And skew is difference in clock arrival time between two registers. For example, we have two registers and the difference in the clock arrival time from the one register to the other register. So this is being handled by the combination logic in between the two registers. And clock insertion delay is delay from clock source till registers. So all this has to be taken care. And if your delay from clock source till register is less, it is good. So now if you see here, you have a clock source, and this is before clock tree synthesis, where you can see that there is a huge delay here, whereas there's a less delay here. So you have to balance it. For that, you add these clock buffers in between. So there are two types of clock tree synthesis being done, which is one using clock tree, one using clock mesh. So in clock tree, the clock buffers are just added in areas where it is required for balancing. Whereas in clock mesh, the clock tree structure is drawn for the entire chip. So this actually will result in more power consumption because it may be drawn in unwanted areas too. So right now, most of the companies have using only clock tree procedure to do clock tree synthesis, so that they can do, so that the tool can add the clock buffers only in the required areas. So how do you achieve a proper clock route? Pre-route of clock nets. So the first route which happens in the design is the power routes, which is done in your floor plan step. The second one is done as in the clock routes. So here the first priority for routing track, and also usage of higher metal layers which are wide width. So as mentioned earlier, metal 5 will be used for clock routes, and also the clock nets are shielded. So you have clock and you have VDD, VDD, ground, ground around it. Now clock tree synthesis includes non-default routing rules. These rules actually consist of double wide or triple wide metal with double wide spacing. So the reason they have double wide or triple wide is to ensure more current flows through it, and clock routes are always using higher metal layers and wide routes. These NDR rules actually should follow the design rules given by the manufacturer, and these rules are used to route only the clock nets and not any other functional net in the design. So after clock tree synthesis, when you open the Innovus GUI, you have an option to check your clock buffer structure. So this is how it looks like, where you can see that the tool has dropped clock buffers in some regions, and when you keep your cursor in these buffers, you can identify the buffer location, the net in which the buffer is being included, so on. And these are the flip-flops in which the balance is good. So it looks like the balance is good now. Clock buffers and clock tree is balanced well. And here you have the skew details, min, max delay details for each skew group, etc. This will help you to analyze if there is any issue in your clock tree structure. Okay, the next step is routing. So what are the goals of a good routing? So routing is almost the final step in physical design. So after routing, the tool is the design is pushed into a few checks, and it is given to the foundry for manufacturing. So goals of good routing is to minimize the total wire length in the design, minimize the critical path delay, so and minimize the congestion hotspots, minimize the number of metal layer changes, and complete routing without increasing the total area of the design. So a good timing closure and meeting timing DRCs. So we need to make sure that less number of metal layer changes occurs in the chip. So how is this achieved? This is achieved by placing the cells close to each other, the communicating channels close to each other, so that less number of metal changes happens. So routing order, as we have mentioned already, first is power routing, where we connect the macro standard cell power pins to VDD and ground. Second is clock routing, which we just saw. All the clocks are given high priority in using the routing resources, and all the clock nets are routed. Third one is a signal route, which happens in the route step. So the signal routes are routed using metal 2, metal 3, metal 4. So the entire routing resources can be used now, as we have completed the clock and power routing already. So routing grids. The routing grids are defined for the entire layout, and routing direction is also defined for each metal layer. For example, we have metal 1, metal 2, metal 3, metal 4. Metal 2 routing will be assigned in the vertical direction. Metal 3 routing will be assigned in the horizontal direction. Metal 4 routing will be assigned in the vertical direction. This is how the routing is being done, and the routing tracks are assigned. So here you have an example. You have a vertical routing track and you have a horizontal routing track. So the nets are routed in vertical and horizontal direction. Okay, so this is actually an example for you to understand the metal 1 and metal 2 structure. So metal 1 routing is done horizontally, metal 2 routing is done vertically. And here you have a standard cell. So you have metal 2 connection and you have metal 1 connection. So this is actually a VR, which is an interconnect between metal 2 and metal 1. And then here you have a VR, and it is an interconnect between this metal 2. So this metal 2 connects to a standard cell pin, and this metal 2 also connects to a standard cell pin. So here the difference between the spacing between these two metal layers, metal 2 layers, is the metal 2 pitch, and the spacing and the distance between these two metal 1 layers is the metal 1 pitch. Okay, so what are the stages of routing? As similar to placement, there are 3 stages of routing here, which is global routing, track assignment, and detailed routing. So global routing happens like this, where traces of routing is being done by the tool, which is not a real route, but it just does a route, and it is not clean, and it has lots of timing and DRC violations. So this is just an approximate plan of routing given by the tool. So what are the objectives of good global routing? It minimizes the overflow of congestion, reduces total wire length, and runtime reduction. So the routing is also timing driven and crosstalk driven. So when the tool does routing, it will take timing into account, and also it will take crosstalk noise into account. So crosstalk noise I will explain to you in the few next slides. So it is timing driven and crosstalk driven. So crosstalk driven routes are nothing but like the tool will try to avoid creation of long paths that run adjacent to each other. So if there are long routes parallel to each other, it will create crosstalk noise. So in order to avoid it, the tool will avoid creation of long paths that run parallel on adjacent tracks. So tracking assignment is the second step. It's the stage where the routing tracks are assigned for each global route, and assigning horizontal and vertical tracks depend on metal layers, and rerouting all overlapped wires. So third one is detailed routing, where you see that all the proper routes are created now. So routing also has three steps as placement, which is global routing, track assignment, and detailed routing. So this is a router database. Like soon after routing, the design will look like this when you turn on the congestion map. So the region at the boundary is the one in blue, and the ones in the center is yellow in color. And here you can see the one in red. So this is the hotspot. So we need to analyze the design and see why we have more congestion in this region. The one in blue can be ignored, the one in yellow can be ignored, but the one in red has to be analyzed and see why it creates congestion, and to see it can be fixed. Okay, so routing, signal integrity is a major part of routing. So as I mentioned earlier, when two nets are when two nets are in parallel direction for a long time, it will create signal integrity issues. So the affected net is called a victim net, and switching net is called the aggressor. So because one net may be switching, so it will affect the neighbor net. So that is why it is always advisable to have not to have long routes for a two long routes parallel to each other. So how do you prevent the crosstalk? You prevent crosstalk by limiting the length of parallel nets, shield specific special nets, and you upsize driver or buffer. So the first, if the first point is taken care of, you don't have to concentrate on the second and third points, because when you limit the length of the parallel net, obviously your crosstalk will be prevented. So soon after routing, you see that you have all the routes. Standard cells are routed, and you have all the connections being done. So your floor planning is done, your power planning is done, your placement is done, your routing is done. And still after routing, you have these empty spaces. So how do we fill these empty spaces? These empty spaces are filled with filler cells. They are actually physical cells. They don't have any functionality in the design. They are used for power rail connectivity and to fill up the gaps between the standard cells. For example, here you have a gap, but here in both the sides you have a standard cell. So when there is a gap, there is a discontinue in the power. So in order to have power rail connectivity, all the empty spaces are filled with filler cells. So these filler cells are added only after the routes optimization. Filler cells contain only N-well, P-well, and power rails. So now you see all the filler cells are added here, and now it is complete, and your route step is complete. So the design is complete, and it is suitable for physical checks and other checks to make sure it passes everything and it can be given to the foundry for manufacturing. So the next step is static timing analysis. So static timing analysis is a very important role in physical design, and most of the companies have a dedicated static timing analysis engineer who works with prime time, the tool, to make sure setup and hold time is clean. So here we will be going through some basics of static timing analysis. What is STA? Static timing analysis is one of the techniques used to verify the timing of a digital design. So timing in the sense it is setup and hold time. It makes sure that our design meets the timing constraints. STA can only check the timing and not the functionality of the circuit. Setup time is the minimum amount of time the data signal should be held steady before the clock's active edge. And I will show you a picture in the next slide, which will help you for more understanding. And hold time is the minimum amount of time the data signal should be held steady after the clock's active edge. Now in this figure, you can see that you have a clock path, you have a data path. So data can toggle in this region, but it should be stable before the clock's active edge. So if it is stable before the clock's active edge, it is setup time. And if it is stable after the clock's active edge, it is hold time. So this is the setup and hold window. So after this area, it can again toggle. So this is how we determine setup time and hold time. So what is the required time and arrival time? Required time is nothing but the time required for data to arrive at a certain point, whereas arrival time is the time at which data arrives at a certain point. So this is the main difference between required time and arrival time. Now, what is a slack? Slack is actually a difference between the required time and the arrival time of a signal. So positive slack indicates that the design is meeting timing, and negative slack indicates the design is not meeting timing. So setup slack is your required time minus arrival time. Hold slack is your arrival time minus required time. And what is a positive slack and a negative slack? Here you have positive slack where your required time is greater than your arrival time, and negative slack is where your arrival time is greater than your required time. So this you will have more understanding when you have look into timing reports and do the analysis. Now, what is a clock latency? So a clock structure will look like this, where you have clock latency equal to source latency plus a network latency. So you have a clock source, a PLL to a clock source point. This is a source latency. The network latency will be your clock source point till the last flip-flop or register. So this actually, it will go through inverters and other networks. So it is known as the network latency. So the combination of source latency and network latency gives you the clock latency. Clock skew is the difference in arrival time of capture edge of two adjacent registers. So positive skew minus capture is the capture clock comes late than the launch clock. For example, here you have a launch clock and here you have a capture clock. So here you see that the capture clock comes late than the launch clock. This is positive skew. And in negative skew, the launch clock, the capture clock will come earlier than the launch clock. You see here, the launch clock comes late than the capture clock for negative skew. So what are the components of a timing path? The timing path consists of three elements, which is the start point, combination logic, and end point. Combination start point will be starting net from a clock group, and it will go through lots of combinational logics, and then it will come to a net, which is an endpoint from a clock group. The start point of the timing path where the data is launched by the clock edge, and it consists of a clock, a primary input, etc. Whereas combination logic, they contain AND or XOR elements. So flip-flop registers and latches are not included in combination logic. So we need to ensure that there are less number of combination logics being included in the timing path. An endpoint is the end of the timing path where data is captured by the clock edge. So what are the types of timing paths? There are 4 types of timing paths. One is input port to register, register to register, register to output port, and input port to output port. So we need to analyze all these 4 types of timing paths. So from the input port to the register, where it is governed by the combination logic, and register to register, which is also governed by the combination logic, and register to output port is also governed by the combination logic. And there is also a type of timing path from the input port to output port. So it has combination logic in between, but it is governed by the placement of input port to IO port. So how do you fix setup violations? Setup violations can be fixed by upsizing the cell. You can upsize the cell, like if you have a cell underscore A2, then you can upsize it to underscore A6 or A8. So the size of the cell will be big, and it will have more drive strength. And you can also include buffers in the design to fix setup violations. You can reduce the clock uncertainty and you can increase the delay in the clock. So, but the basic idea to fix setup violation will include the first 2, where you upsize the cell and also you insert buffers. And when you fix hold violations, you can add delay and also detour the routing, and you can downsize the cell. But we need to have proper knowledge, like if you downsize the cell to fix hold violation, it should not affect your setup violation. There may be some path which may fail both setup and hold. There you will have a big problem in fixing timing, because when you try to fix hold, when you check setup will fail. When you fix setup and you check hold will fail. So we need to understand the balance, the margin, and play accordingly. So this is a prime time timing report where you have start point, end point, and you have a net here from the clock, I clock, and path type is max. Max means setup time and min is hold time. Here you see positive slack equals required time is greater than the arrival time. So you have a positive slack. If your required time is less than the arrival time, then you have a negative slack. Here you have a path which is met. So met means it is already meeting timing. You have an endpoint, begin point, and you have a path group which is clock underscore W underscore 4. So you have a required time, you have a slack, and you have an arrival time. Required time equal to phase shift minus setup plus other end arrival time. Arrival time is obtained through all the flops. Here your whole timing report where it is violated. Your slack is arrival time minus required time. Here you see your endpoint and begin points are here with your clock group is clock W underscore 1. And here your required time equals the other end arrival time plus hold plus phase shift minus the cycle adjustment. So this gives you your required time, and your arrival time is from the combination logic being added. So when you see your arrival time, it is 0.117. So your slack is minus 20 nanosecond. So this actually fails your timing. So this is actually a basic understanding of how to analyze a timing report. So this will actually help you when you work on a real-time project. Okay, the last module for today's discussion is physical verification. So what are the checks in physical verification? Design rule check, layout versus schematic, electrical rule check, and XOR and logical equivalence check. Design rule check is to check DRC violations. Layout versus schematics to check LVS. Electrical rule check is to check ERC. So DRC is a design rule check is a process where the physical design database is checked against design rules. These design rules are provided by the manufacturers to the design engineers. So DRC should be clean before the chip is passed to the foundry. Because once we provide the data, the output from physical design team to the foundry for manufacturing, they will also run all these checks at their site to make sure that we give them the right data. So what are the types of DRC violations? We have minimum width of a metal layer, shorts, minimum spacing of metal layer, minimum width and spacing for vias, minimum area, wide metal jog, and different net spacing. Here, this is an example for a short violation. Here you have horizontal net in light blue, vertical net in purple color, and here you see that this is a different net name and this is a different net name. They all short together because of the same metal layer. So how do we fix this? We need to extend this here so that it will actually fix this violation, because this net will be removed, so the short is fixed. And there is a spacing violation here. Here there is a horizontal net and a vertical net in pink, a horizontal in brown. So when the two nets combine together, the tool will drop a via, which is the interconnect. So this via is creating spacing violation with the net. So how do we fix this? We can change the type of the via. So this will help you to fix the violation. And here also you have an example for spacing violation, where you see that you have metal 2 and metal 3 in vertical direction. So here you have spacing between this via, this via and the pin shape here. And here you have a spacing between this metal 2 and this metal 2. So how do we fix this? We can bring this metal 3 to this region so that all the spacing is resolved. So bring it here, and then you convert it to, when you change it to metal 2, you will add a via here. So this will fix the spacing violation in this region. So min area violation is the other violation, where you have metal 3 in vertical direction and a metal 2, 3 via is drawn. So this structure also resembles the same this structure, but you see here that here you don't have violation, but here you have violation. Why is it so? Here, if you see that you have metal 3 and you have a via and you have a metal 2 structure. So this metal 2 structure is not present here. So because of this, we have the problem that when you drop a via, the via should have a particular area for it to be placed. So that here you have a metal 2 and here a metal 3. Here you have metal 2, 3, but here there is no extension of net. So when you extend the metal 2 to a certain region, this violation will be resolved, so that the minimum area to place the via is met. So what are the basic DRC checks? There are 3 basic DRC checks. One is width of the metal layer, spacing of the metal layer, and also enclosure of via. Next one is the layout versus schematic check, which is LVS. Here you have GDS, which is an output from physical design, and the schematic is an output from the initial front-end team. So the extracted netlist is from the GDS. The source netlist is from this schematic. Source netlist is the one we used as an input for first step of physical design. So when you compare these two netlists, the tool will generate a LVS report, and the LVS report should be clean, so that it ensures that your layout and your schematic is matching. Layout is your physical design output, and your input of physical design is matching, so that even though the tool has undergone lots of optimization and steps in physical design, the layout and schematic is still matching and no change in functionality has happened. What are the types of LVS errors? Shorts and opens, and also unbound pins. For example, if the pins don't have any physical shape, but they still exist in the netlist, then it is an unbound pin. So here you have an example for an open, which is the buff net, and this net is open here. So when you extend the connection, it is fixed. And this is also an example for a short. So how do you fix this one? You bring this net to this region and it will fix the short. Electrical rule check. Electrical rule checking is a methodology used to check the robustness of a design, both at schematic and layout level. ERC helps to check floating gates, floating interconnect, metal and poly, shorter drain and source of a MOSFET. So if the design has floating gates and floating interconnects, ERC check will help you to identify it, and we need to make sure that we fix it. XOR check is run when the original and modified databases are compared. For example, if you have released a chip and your chip has 6 letter layers, the chip is being released to the market, and after 1 year, the customer comes back to you for a change, for an addition feature, and he mentions to you that you have to make the changes only in metal 2 and metal 3. Now, even though you have 6 metal layers, your fix should be only in metal 2 and metal 3. So you do the fix, but how do you confirm that only metal 2 and metal 3 has been changed? Because each change in layer will cost millions of money for the customer. So how do you confirm that only metal 2 and metal 3 is being changed? You do an XOR check. XOR check is you compare the two GDS and you make sure and you get a report. So in the report, you check that what are the changes. The tool will report only metal 2 and metal 3 as change of layers. What if the tool reports metal 2, metal 3, and metal 4? In that case, we have to and again go back to the design and see what has happened for metal 4 to be changed. But by the customer's request, only metal 2 and metal 3 has to be changed. So we go back to the design, we fix it, and then we again do XOR check to ensure that only metal 2 and metal 3 has been changed. So this is a very critical check we have to do as a physical design engineer to ensure that only the metal 2 and metal 3 is being changed. So all the checks in physical design are very critical ones, and we cannot take it for granted, because it will create a lot of issues at the end of the day if it is not done properly. So logical equivalence check. This actually is same as LVS, but LVS is layout versus schematic, but this one is it just compares the two netlist. So the output from physical design, which is the output netlist from physical design, and the input netlist for physical design is compared in logical equivalence check to ensure that even though we have done lots of changes in physical design, to the functionality of the design is still the same, and it doesn't change the function of the design. For example, this logic equivalence check is done in many stages. First the RTL is given and RTL gets modified, and so they check whether it is logically equivalent. And after RTL modification, gate level netlist is synthesized. So again, it is checked for logical equivalence check to see whether it is synthesized correctly. And then after we get the place and we get the netlist for physical design, the output from physical design is a place and route netlist. So again, logical equivalence check is performed to make sure that even after CTS, even after adding repeaters, buffers, even after place and route, which is like routing, clock tree synthesis, and optimization, is the function still the same. So all these checks are done stage by stage to ensure that nothing has changed. So this is a very critical task, and physical design is a very challenging market, and there is a lot of demand for different types of VLSI engineers in the market around the globe. But the job is a very challenging one, and it requires more concentration and more knowledge of the basic ideas behind VLSI. So this brings us to a closure of VLSI and physical design. And now let's look into few slides like how is life in VLSI. So there are some online certification courses available for VLSI in India and also abroad. So all these help to attain a VLSI certification when we go into the industry for internship or for higher studies. It is a very useful um, certificate, and it gives you more in-depth knowledge with hands-on to obtain this certification. And there are VLSI studies and internship available in India in IITs, NITs, BITS, Bilani, and some top universities. VLSI research labs are available, and there are even positions for research assistants with professors from IITs and NITs. And VLSI studies and internship abroad, they are available in NTU Singapore, NUS Singapore, which is Nanyang Technological University and National University of Singapore, German Institute of Science and Technology, which offers a joint degree program with Nanyang Technological University and Technical University of Munich in Singapore, and University of California, MIT, Stanford University, and so on. So all these universities provide internship, provide master's, PhD programs in VLSI. And there are some more universities in US who also offer studies and internship. Okay, so what are the job roles in semiconductor industry? We have design engineers, we have verification engineers, application engineers, and manufacturing engineers. Design engineers include front-end engineers who design the circuit and also do the Verilog VHDL coding. So they are the engineers who take care of the first half of the IC design flow, and the back end of physical design engineers are the engineers who take care of physical design. And FPGA engineers are the field programmable gate array engineers who take care of the FPGA coding. And like Xilinx is a very good company for FPGA. And DFT, designed for testability engineers, who take care of scan chain insertion, all these details in the netlist. And analog and mixed signal engineers, radio frequency engineers, IP design engineers. So companies hire engineers just for IP design alone. Design engineer, verification engineers are working at front-end verification. So once the circuit is being designed by the front-end team, there is a front-end verification team who will run verification processes to check whether their work is correct. So there are EDA tools validation engineer and also IP verification engineers. And there are application engineers in the EDA tool companies. EDA tool companies like Cadence, Synopsys, Mentor Graphics are all EDA companies where they design the tools, develop the tools for IC design. So they have application engineers who are corporate application engineers and also field application engineers who will be going to various companies to promote their market their tools and also to debug issues when their tools are being used. And there is manufacturing engineer who plays a very important role in manufacturing the chip. So they are the foundry or fab engineers, they are the fab managers, they are the tech support guys, and also the clean room technicians and engineers. So they wear the white dress and they work in the clean room. So these are some roles, job roles in the semiconductor industry. And so VLSI is a very big market, and there are lots of job opportunities in the recent times. There are lots of educational programs in YouTube, and also to discuss in-depth details of complex definitions in VLSI. So what are the major recruiters in the field of VLSI? We have ST Microelectronics, MediaTek, which is a Japanese company. Infineon is a German company. TSMC is is a manufacturing company along with the design house. It is in Japan. NVIDIA is a US company which is more into graphics processors because nowadays lots of laptops and gadgets which come up with graphics include NVIDIA in it. Qualcomm is a US company. Texas Systems is a very old US company. Intel, as we all know, is a giant in the field of IC design electronics. So Xilinx is a company in US which is more into FPGA programming. NXP is a German company. Micron is a US company. Broadcom is also a very big giant in the field of IC design VLSI. So they have their headquarters in US, and Broadcom and many other companies over here. They also have their design centers in Bangalore, Chennai, Noida, so on. And Cypress Semiconductor is also a very big company, which is a major recruiter. So there are also EDA companies like Cadence, whose tool is being used for physical design and also other analysis tools. Pentographics is also an EDA company, and Synopsys is also a EDA company. So all the all the above companies are product companies, whereas the last three are the EDA companies. So they take care of the tools being used in the industry. So the engineers who are hired for these three companies at the bottom are expected to develop the tool to debug the tool being used for IC design. Yes. So with this, we come to an end of today's presentation on VLSI physical design. And you can write to me or you can contact me through LinkedIn for more information and details. And I hope that this session was useful to each one of you. And I wish you all the best once again. Thank you.
Dear participants, if you have any queries or doubts, you can ask to our resource person. Otherwise, you can put your query in our chat box. Once again, dear participants, professors, if you have any queries, you can ask right now. So there is an option for unmute your mic. So with this, you can ask your queries. Samuel sir?
Yes, sir.
I think there is no more queries, sir. Let the wind up session, sir.
Yeah, that's all. Thank you, sir.
Thank you, sir. Thank you for your nice presentation as well as explanation. We
Yeah.
need your fullest cooperation for upcoming cases also. Still, we are going to have two more cases regarding VLSI, FDP,
Sure.
SATP, sorry. So we need your presence, sir, in those cases
Yes, sir,
also.
sure. And once again, thanks to Kongunadu College of Engineering and Technology for inviting me today as a speaker during this online short-term training program.
Okay. Thank you, sir. Thank you so much, sir.
Thank you, sir.
Dear participants, day 4 session 1 attendance come feedback link will be available in our chat box. So you can put your presence using this link. The link will be activated up to 30 minutes. Thank you.
Dear participants, the day 4 session 1 attendance and the feedback link is posted in chat box. It will be open up to 30 minutes, so kindly fill it soon. And all the recordings of this FTP we will share at the end of this FTP. Thank you all.